Okay, here's another function. This one is really kind of strange. There's probably no reason at all for you ever to come up with this one in your life, but I want to show it to you because it just illustrates a few interesting things about functions and some of the theorems that we've looked at. So maybe you're getting used to it. You will after the next two or three anyway. We'll go them through the same 4 or 5 steps. First step is to ask what's the domain. And in this case, again, there's no restriction. So there's no denominators, no logarithms, and so your domain is everything. Secondly is intercepts. First of all, we see that f of 0 is equal to 0. So, so the y-intercept is the point 0, 0. To get the x-intercept, we again set the function equal to 0. And this could be a bit of an algebraic challenge. How do you go about determining where this thing is equal to 0? You have x to the 2/3 power minus x. Okay, what about that? Well, here's what I would do. I would factor out everything possible. So you can factor an x to the 2/3 out of both of these. You're left with here 3 there. Here you're going to be left with x to the 1/3 power, which of course is the same as the cube root of x. And that's all equal to 0. And so there's two places where this thing could be 0. Either when x is 0 for this one, or when the cube root of x is 0. Whose number, for what number is the cube root of that number equal to 3? Did I say 0? I meant 3. Well, when is the cube root of a number equal to 3? Or in other words, this number would be the cube of 3. The cube of 3 is 27. So you have two choices here, either when x is 0 or when x is 27, because the cube root of 27 is 3. So here we go. Remember this routine? So we're going to put a 0 here, a 27 here, and again, we'll just take values on all sides. Take 250,000. That's cube root of that is a pretty decent sized number, so 3 minus that is negative. That's going to be positive. Positive times negative is negative. Nice number between here. How about 1? Cube root of 1 is 1. 3 minus 1 is 2. Positive, that's positive. And finally put in, how about negative 1? The cube root of negative 1 is negative 1. 3 minus a negative 1. 3 minus a negative 1 is 4, so that's positive. Here you're taking the cube root of negative 1, which is negative 1, but then you're squaring it, so that's positive. Positive times positive is positive again. So there's what the function is doing. Let's see. What else is there? There's symmetries. If you take f of negative x, you're going to get 3 times negative x to the 2/3 power minus a negative x, which is the same as 3 times, sorry, that's kind of sloppy, negative x. If you take negative x and square it, it's going to become just a positive x. So this is positive by the time you're done with it, x to the 2/3, and this is negative of a negative is a positive. So you look at this thing and you say, is it the same as that? Nope. Is it exactly the opposite of that? Nope. So there's no symmetries. Okay. And then finally, I guess we want asymptotes, don't we? So there's asymptotes. Vertical, none. We'll get to one eventually where there's some vertical asymptotes, but there's no denominators here. Horizontal, we're basically asking again, what's the limit of this function as x goes to infinity? So what's happening? And let's do the same thing we did with a previous problem, well, or what we did right here. We're going to factor the x to the 2/3 out. And we're left with 3 minus the cube root of x. I'll write it like this again. Okay? So what happens? As x gets to be a big positive number, this is all going to be positive. This is going to be a big positive number, but you're subtracting it. So when you subtract a big positive number, you get a negative number. So negative times positive is negative. And so that's going off to minus infinity. What happens when you do the same thing but x is going to minus infinity? Well, let's see. This is still going to be positive because you're squaring it. Here you take the cube root of a negative number. Cube root of a negative number is negative. Negative of a negative is positive. So this is positive and that's positive. Multiply two positives and you get a positive again. So that's going off to positive infinity. So you get all that. Okay? Wow. Going to have to figure out how to make use of our space here. Okay, so there's that one. Now we find out where it's increasing or decreasing. So we'll take the derivative. Let's go right back to the original form for the derivative. F prime of x is going to be what? 2/3 times 3 is going to end up with a 2 in front. 2 times x to the, what do? You subtract 1 there, so it's going to be negative 1/3 power minus 1. Okay, derivative of x is 1. So let's see, what do we do there? Got some options again. Let's go ahead and just set this equal to 0. This seems to be the natural thing to do, is to set this equal to 0 and then set this equal to 1. You're going to get 2. I'm going to write it as 2 over the cube root of x, which is what this is equal to 1. And then if I multiply both sides by cube root of x, I get cube root of x is equal to 2. And so x is equal to 8. So there is a place where the derivative is equal to 0 when x is equal to 8. So if I were doing this with you in a classroom, I've taught this enough that I'd ask, are there any other critical points? And the answer would typically be 0. That's the only place where the derivative is 0. And then we'd go ahead and try to graph it. And in trying to graph it, we find that it's impossible. And if I had enough time, and if I had another whole big board behind me here, we'd go ahead and go down that route. Here on a video lesson, I'm going to have to just tell you right up front, here's the other thing you have to worry about. This thing right here is, again, 2 over the cube root of x. That's what this means. So it's 2 over the cube root of x minus 1. Okay? So you've got an x in the denominator. There's a place where the derivative does not exist. Since that's such an important thing, let me write it a little bit better. 2 over the cube root of x minus 1. There we go. So you've got an x in the denominator, and dividing by 0 is undefined. So you have another critical point at 0. So yeah, there's where the derivative is undefined, and here's where the derivative is 0. So you'll see how this all works together here. So here's 0. Here's 8. Those are your two critical points. Let's check all sides of them. So here's our derivative again. So let's stick in some values. If you stick in 1,000, you're going to have 2 over the cube root of 1,000. That's going to be a small number. Minus 1 is going to be negative. 1 is a real easy number in here to put. The cube root of 1 is 1. So 2 over 1 is 2. 2 over 1 is 2. 2 minus 1 is 1. 1 is positive. So it's positive there. And then to the left of 0, put in a negative 50. This is going to be negative. You're subtracting 1. It's all going to be negative. Okay? So let's get rid of this now. We don't need it anymore. Well, actually, I did need that part, didn't I? That was a 27 there. Okay. And so anyway, this is the derivative. This is f prime. So if f prime is negative, that means the function is decreasing. If the derivative is positive, that means it's increasing. And here it goes back to decreasing again. Are you with me? Now, I think we still have enough room here to do the second derivative. So the second derivative, here's the first derivative. Let me rewrite that now as 2 times x to the negative 1/3 minus 1. And so now when I take the second derivative, it's going to be, watch out, you bring this down, so it's going to be negative 2/3 times x to the negative 4/3, right? You subtract 1 from that, and you're going to get x to the negative 4/3, and the derivative of 1 is 0. So this is the same as 2 over 3 times, however you want to write it. You can write it as the cube root of x to the 4th. I don't like those fractional exponents. I like to write them as cubic things and put them downstairs so that I get rid of the negative, and it just helps me visualize what's going on. So there it is again. Notice that this thing is undefined at 0, so we'll see what that does for us. But in particular, notice that on both sides of 0, there's a place where this thing isn't defined, but other than that, if I put in any value of x, it's going to be positive on both sides. See that? Let's see. Oh, negative on both sides, sorry. I have a negative there. Negative on both sides. So it's going to be negative here, negative there, which means it's concave down here, and concave down there. So now, let's see what this thing looks like. And I guess this is my widest spot. Let's start like this. And decide where to draw. Go like this. Like so. And I'm going to have to squeeze everything together. So this is going to be my 8. What other interesting 27 I've got. Here's 27 right there. Okay, let's see what's going on. Until you get to 0, what's happening? First of all, notice it's going to be positive. The function is, it's going to be decreasing, and it's going to be concave down. So until you get to 0, it's positive, it's up here. It's decreasing, so it's coming down, and it's concave down, which means it's going to look like that. Okay, and 0, 0 is a point on it. Then what? Once you pass 0, it starts increasing. It increases until you get to 8, and it's always concave down. So it's always concave down, so it increases until you get to 8, concave down, and then it starts decreasing. Once you pass 8, it starts decreasing, still concave down, and it slices through a 27. So something like that. Okay, so there's the graph of it right there. Kind of unusual. The reason I like this one is notice that you've got a relative maximum right there at the point 8. What's the value of the function at 8? If you put 8 in here, take the cube root of 8, you get 2. 2 squared is 4. 4 times 3 is 12. 12 minus 8 is 4. So that's kind of nice. That's just the value 8, 4 right there. And here is the point 0, 0. You've got a relative minimum there. This is a place where the derivative is 0. This is a place where the derivative is not defined. Notice the difference. Nice and smooth there. You have a tangent line. Here's your tangent line right there. Here you have a billion tangent lines, okay? There's no unique tangent line, and that tells us that there's no derivative there. So concave down, concave down. This is a hard one for students to do because they just can't even imagine what this thing looks like, but there it is. So it's going down to minus infinity. That's what we said, right? Let's see, where did we all do that stuff? Yep, it's going to minus infinity as x goes to infinity, and as x goes to minus infinity, see this? As x goes to minus infinity, the function's going off to infinity. So it goes up like that. Okay, and the last thing we want to do is remind ourselves about the mean value theorem again. What does the mean value theorem say? Recall it says something like this. If you have yourself a differentiable function between two points on a certain interval, then you first find this average slope, and whatever that average slope is, that's going to occur somewhere in the middle, somewhere between those 2 points, at least once. Okay? So if we apply it to this particular function, notice that if we look at the value at -1, f of -1 is going to be 3 times 1 minus the -1 is 4. So that's going to be 4. And when you stuck 8 into the function, you got 4. Okay? So in other words, the average slope between these two values of the function is 0. Okay? Does that look like 0? Pretty close. Okay? That slope is 0. So according to the mean value theorem, I'll ask this as a question. Do we need to be able to find some point in here between -1 and 8 where the slope is 0? Doesn't look like there are any. Here the slope is negative, and then here the slope is positive. So we're out of luck. Did we find a counterexample to the mean value theorem? And the answer is no. The mean value theorem is only guaranteed to work when we have a function which is differentiable everywhere on that interval. That is, the derivative exists everywhere on the interval, and that's not the case here. The derivative doesn't exist at 0, and so all bets are off. The mean value theorem doesn't apply. So it's a nice example. That's another reason I like doing this one. It shows when you cannot use the mean value theorem. So hopefully another good interesting graph to do in the next lesson. It's good.